Here's a brief introduction to our project. We have developed a self-balancing underwater robot powered by the Navio 2 board and Raspberry Pi. The robot utilizes IMU data to estimate its orientation and applies a geometric PID controller to maintain stability in challenging underwater environments. But due to several challenges we have faced, the demonstration would be limited to showcasing PWM outputs corresponding the orientation changes.
Here are our objectives: accessing sensor data, using PX4 and Navio libraries, designing a PID controller for stabilization, obtaining PWM outputs, debugging, and demonstration. Moving on to methodology, first we installed MLID Raspbian OS, which is compatible with Navio 2, then obtained sensor data using PX4 and existing libraries. After that, we designed Madwick filter to obtain accurate sensor readings. Then the PID controller was designed. Finally, the resulting PWM outputs were plotted for clear visualization of results. Moving on to results, here are the sensor data we obtained through PX4 and Navio libraries. It shows the readings from 9-axis IMU, which consists of the accelerometer, gyrometer, and magnetometer. Based on the ROV's thruster configuration shown in this figure, motors 1, 2, 3, and 4 are responsible for yaw control. Motors 5, 6, 7, and 8 are responsible for pitch and roll control according to our design ideology. Here is a demonstration of the PWM outputs we have obtained by changing pitch, roll, and yaw. At the beginning of the video, the ROV is placed in its reference neutral position. In this state, there are no changes in roll, pitch, or yaw, indicating that the system is stable. As a result, the PWM outputs for all motors remain constant, with no variation observed. This confirms that the controller maintains steady motor signals when the ROV is at rest and properly oriented. First, we are changing in roll positive direction. PWM outputs for motors 5, 6 should increase while 7 and 8 should decrease in this situation to achieve stabilization. If the roll is changed in negative direction, outputs should be inversely occurs. After that, we are changing it to the initial reference position. After that, we are changing pitch in the positive direction. PWM outputs for motors 6, 8 should increase while 5 and 7 should decrease in this situation to achieve stabilization. If the pitch is changed in negative direction, outputs should be reversed like what happened in the roll. After that, as usual, we come back to our reference place. At last, we are changing yaw in the positive direction. PWM outputs for motors 1, 3 should increase while 2 and 4 should decrease in this situation to achieve stabilization. If the yaw is changed in negative direction, outputs should be reversed. Then we come back to our reference point again. So, it's clear that our PWM output correctly compensate for the changes in orientation. Hence, it is proved that autonomous stabilization could be achieved by this approach. We encountered several challenges while doing this project. One of the main problems was the Raspberry OS corruption. Due to OS corruption, we were unable to get sensor data. We overcame this by reinstalling the Navio OS, restoring full control and functionality of the robot. Next, we faced several issues due to failure of the batteries. It prevented motor power-up, but we were able to generate PWM outputs by connecting to the boards. This setup allowed us to test the ROV's stabilization behavior without running the motors, relying solely on orientation feedback and PWM signal responses. That concludes our project demonstration. Thank you for your time and attention.